Hi again, everyone. Before we left it, where I was going to start explaining how to record LFPs and plot LFPs and CSDs, current source density. So I'm gonna, for that, I haven't actually moved that to the Google Colab, but it's just a pretty simple example. So I'm just gonna show it from the website. Right down here. So here, this is tutorial 9, and it explains basically the only simple step you have to do to record LFPs, and that is essentially to add this. Where's the code? Here. So here's an example code, and what you have to do is add this line. So in simconfig, you have to tell NetPyNE that you want to record LFP. And essentially what you have to put here is a list of coordinates, 3D coordinates, where you want to place the electrode. So I think I mentioned before that the LFP recording or LFP simulation in NetPyNE is done using this thing called the line source approximation, which essentially sums all the membrane currents of all the segments of all the neurons, and it scales it by 1 over the distance to the electrode, which is, I think, one of the most accurate approximations for LFPs. It doesn't take into account, so it assumes an homogeneous space inside the tissue, and there are ways to make this a bit more elaborate, but they involve sort of changing more of the NetPyNE backend code. But for now, this is the method also used, for example, by the Allen Brain tool, and it's the standard method, I believe, for the LFPy tool, which is focused on this kind of analysis. So if you include this line, and then if you just plot, either include the plot LFP function in the analysis here in the simconfig, or if you call sim.analysis plot LFP, you will get, let me see, right here, this kind of, oh, I clicked away. You will get this kind of figure. So there's 2 examples. There's a link here in the website that says Lfe Recording Example. This is a GitHub folder, and it has 2 examples. One is with a single cell, and that's a morphologically detailed cell that you see here, and it just generates a spike. And so what we did is place a number of electrodes, as you can see here. One of the plots that you get is actually the location of the electrodes in 3D space. So you see here you have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we place 9 electrodes along the sides of the cell, the neuron, and then we trigger a spike in the neuron. This is the spike in a very extended stretch timescale. And so we measure what the electrodes are measuring. And you see that the electrodes that are closer to the soma, 6 and 7, those are the ones that pick up the signal more strongly. Of course, the strongest peak goes downwards because we are measuring from the outside of the cell. So the polarity of the electrical signal is opposite to the spike inside the cell. And as you move away from the soma of the neuron, the strength of this LFP signal becomes smaller. Of course, if you had like a network of many neurons and they had synaptic inputs all along this dendrite, then you would pick up also those synaptic currents that are modifying the membrane voltage. In the case of the network example is the same we've seen a couple of times, the one that has all these 3 layers, 50 neurons in each layer, 2 populations of excitatory and inhibitory cells, and the morphology is like 5 compartment cells. So usually to get realistic LFP signals, you need at least some kind of multi-compartment cells. If you try with point neurons or single compartment neurons, you won't really get much of a good representation of the LFP from what we've seen. but in these 5-compartment neurons, it usually works okay. And this example is not really meant to show anything too interesting, but you see at least an example of the different plots that you get. So this is the raw signal. This is the first plot you get. The raw signal at each of the electrodes plus the average of all the electrodes. Then you get the power spectral density. If I can zoom in. The power spectral density. So the strength of the different frequencies for each of the electrodes. So here we see that it's mostly these low frequencies that have the strongest power. But when you move down the layers, you get a strong gamma oscillation here at 40 Hertz. And you get the spectrogram. This is actually an old representation of the spectrogram. Now you get like a nicer signal that I can try to show here. And you get this other figure shows the transfer resistance to the electrode. So it's a measure of this component of the equation that we're using to calculate the LFP that shows the transfer resistance from the electrode itself to each of the neurons, to each of the segments in the neurons. So it basically indicates you how much effect these segments are having on the electrode. You can also see that here.
Salvador, can I ask you something?
Yeah.
I was wondering what is the method to choose the placement of the electrode in this case?
Now, no specific method. So we just place them wherever we thought were reasonable for each case.
Okay.
But usually you would do, if you have experimental data that you're trying to compare to, then try to place them as similar as possible to the experimental data. You usually see this is quite common to have like at multiple depths. Something common is quite at 100 micrometers interval.
Okay.
So you have spacing of 100 or 50 or something like that, and that also allows you to calculate the CSD signal. But yeah, again, depends on the experimental data.
And I can add more or a specific quantity of them. Yeah, because I was thinking about maybe recording a lot of those electrodes so I can relay the signal. So in this case, the LFP with a more fancy multi-dimensional analysis. And
yeah, that would be interesting. And yeah, you can put as many electrodes as you want in any place you want.
So I don't have any limits in this. Okay, yeah, and spatial limit.
The sky only.
Okay.
So, and I wanted to show the latest implementation of the SLFP spectrogram, which is a bit better. I'm sorry. So we are now, before we were using an FFT method, and now we've switched to this wavelet method to calculate the spectrogram, which provides a bit more of an accurate result. And this is the screenshot. I'm pasting it in only tutors. So it has a more clean representation. And I think there was another question. The LFP calculation requires a tissue conductance, right? What is the default conductance? For example, is the conductance of brain tissue, CSF, or water? I believe it's the conductance, something between brain tissue and CSF. The value, I think, is 1.5 or 1.2 or something like that. I can check it, but it's the default value they use in these tools. So in LFPy and in the Allen Brain tool, they use the same value.
I have a comment about the Sebastian questions. I think if you want to do a fancy mathematical analysis about the neural activity, you have more data analyzing the voltage at each point of neuron. And when you average in an LFP, you are losing information for a very detailed analysis. And there are all other methods to compress information from multidimensional to less dimensional or something like that.
Yeah, a comment about it. Yeah, it's true. You lose some data, but the point here is that if you have a bunch of neurons, you actually don't have the computational power to calculate those kind of measurements. I mean, it's quite common just to do this kind of stuffs, but pairwise. That what is really easy. But the point here is just to take 3 or more signals and try to calculate some statistical analysis from them. And that is quite hard to calculate. That's the point. If you take all the neurons, more than 1,000, it will be quite complicated to calculate it. That's why you take as a sample of the LFP of the neurons around the sensor.
But if you will do a sample, maybe could be another method of sampling inside a whole tissue. You can literally measure everything in a random sampling or something like that, and not just like a line of electrodes as in experiments.
Yeah, I got it. Yeah, that's why I'm quite interested in this kind of approach, because it's an approximation of the whole activity and not a raw analysis of each neuron and each signal. That will be ideal, but it's not possible in this case. Yeah, but I get your point. Thanks.
So actually, I think it's both are interesting, and even relating both of them. No? So doing some kind of analysis at the single spike level and then at the LFP level, and seeing how they compare as well, because that's useful for experimental data where you only sometimes have access to the LFP and you want to know information about the underlying more detailed dynamics. So you could potentially extract information from the LFP.
Well, that is an interesting work, an interesting idea, but yeah, I will think about it. Thanks.
Okay, and I'm trying to show the CSD function, but I'm getting an error. So Erica, who actually implemented the CSD function and is giving the exercises session this afternoon, I'll ask her to show you the CSD function, which is really nice. And again, this is like the second derivative of the LFP, so it shows some interesting components as well, and it's very useful to compare to experimental data. So for example, with our collaborators here who have macaques studying auditory cortex, all their analysis is done using CSD, current source density. And so we generate that from our models to compare with their data. Okay, any questions about this? Okay, so I now want to move on to this idea of the internal structures and representation of NetPyNE, so that you understand a bit more how things are organized internally and how you can access the different components. I think that's something that in the past we haven't really touched that much, and it turns out to be very useful. What is CSD used for? Well, it's another representation of the dynamics in the network. It gives you like the sinks and the, how do you call them? So where the currents go in and when the currents go out of the cell, basically. And so, for example, let me see if I have a figure here. Well, actually, Erica will show you some of this stuff this afternoon and even tomorrow morning, talking about the A1 model. So, okay, so I'm gonna present this slide, and I'm gonna go briefly over this, and then I just wanna switch to playing around with these things on Google Colab, including importing cells, and we're gonna see the structure of the imported cells and how it looks. Okay, so I think I mentioned this before. So NetPyNE is really just a Python package, and it's divided into a number of sub-packages that have functionality for the different things you can do in NetPyNE. from analysis to batch to things related to the cell, network, plotting, and so on. You saw this diagram yesterday as introduction, so I just wanted to relate some of the sub-packages to the different components. And the first one, probably the most important, where the NetPyNE language is defined, is in the package sub-package specifications. And here you have the definition of these two main objects, the net params, or the net params class, and you create objects of the class net params, and the class simconfig, and you have to create an object of the class simconfig. We also have this package conversion that handles all the stuff related to importing neurons from other, from outside, from Neuron or from NeurML. The network instantiation, so creating actually all the neuron objects required to simulate the network, and that is done in this sub-package called network. And you have usually work in NetPyNE with an object called net, which is of the class network. And inside this object class of this object called net, you will have all the cells, all the connections, and so on. For example, yeah, the list of cells is inside net.cells, and each cell is in turn of the class network cell. Okay, so we have like a hierarchy here from net to cells, each one with its own class. So in NetPyNE internally is quite object-oriented, even though it has a declarative language. So sometimes people say, why didn't you program this as an object-oriented tool with all the methods? And so in a way, we do have that representation, but internally, once you generate the network instance. For the simulation, we have the package sim, and the output of the simulations are stored in this dictionary called sim data. And I also have a look at that dictionary in a bit. So this has, for example, the spike times, has the voltage recordings. So of course, all this data, you can play around with it in Python if you want to have any other representation or analyze it in some other way. You're free to do that in Python, accessing these data structures. This data is also saved to file. So when you select the type of file you want to save to, JSON, picto, or whatever, you will get also the sim data as well as the network. For analysis and visualization, we have two sub-packages, analysis and plotting. Right now, it's actually all combining to do analysis, but we are splitting it in two. And the next versions will have this separated. And for exporting, again, we have this conversion package, as well as some of the functions are inside sim for saving to objects. For these batch simulations, for parameter exploration and optimization, everything is inside the sub-package called batch. Okay, this was just an example to show the typical structure of NetPyNE in terms of when you define a model at the beginning, these high-level specifications that we call, and a bit of the structure of these two main objects that you use for the high-level specifications. You have the net params object and you have the simconfig object. Inside net params, as you have seen, you have 7 main attributes, which in turn are dictionaries. They're actually a special class of dictionary called ODict, which is derived from Python's ordered dictionary, which is a dictionary but keeps the order of the elements. And it's a special version that we implemented in NetPyNE to allow for this dot notation that I showed before. So dictionaries, you usually have to do the square brackets and quotes, but this special type allows you to access the dictionary using dots, like if it was a class. This sometimes can be a bit confusing, and we don't really use it much, but it's good that you know it. So the net params object, apart from these main sort of subcategories to define the network, they also have a bunch of variables, like the size of the network, size X, size Y, size Z, that we saw before. And that helps to define some other properties of the network. The simconfig object, in turn, has a bunch of attributes, and these are usually single-valued or maybe as a dictionary, like record traces. But in general, the structure of sim config is much simpler, much more plain than the net params, which is more nested. This is again describing the 8 components of net params that we have seen. We haven't really touched much on the subcon params, although I've mentioned what is the purpose of it, and I will share some examples. And this is another presentation of the same thing. So for each of these components of net params, you basically have some dictionaries that contain the definition of the net. This I'm not going to go into detail, but just wanted to show you that we do have like a lot of methods inside NetPyNE that can be used by users, although they're not very common, but they are there. So in net params, for example, each of these components, for example, cell params, you can use object-oriented methods to fill them in. So instead of writing the actual entries of the dictionary by yourself, you could use a method. And for some, for example, for the GUI, this is preferred because it's always preferred to use methods that can debug errors. So you can define the network also using these methods. I personally think it doesn't really add much at this point, but it's also an option. Let's do this one. In terms of the API, so the application programming interface for NetPyNE, the things you can do by calling methods, the main ones are shown here. So this is in what we call the wrappers, and they're accessible directly through the sim object. So the one we've been using until now is create, simulate, analyze. And that does everything. So it creates the network, instantiates the network, runs the simulation in parallel, and runs any analysis that you have specified in sim config. But you have a bunch of other wrappers, like you might want to just create and simulate, but you don't want to analyze. So you call this one. You might want to do the steps separately. You want to create, then maybe you want to modify something in the network before running, which is quite common. And then you want to simulate, you can call this one, and then analyze. Okay, so you can play around with these different methods to personalize what you want to do with the model. Sorry. And you have a couple of special ways of simulating the network. So this one says interval, create, simulate, analyze. I think it might have been renamed, but the idea is that it runs the simulation at intervals and saves every X interval that you specify. And the purpose of this is when you run very long simulations on supercomputers, for example, to avoid losing all your information when you are, if it crashes, which is not uncommon, and you're running for 3 days and then it crashes. So to avoid crying, you can save your simulation at intervals, and you will get at least some of the data that you can use. And yeah, you have a couple others. For all these methods that are shown here on the right are more sort of used internally by NetPyNE, but they're available also to the user. If you are a more experienced user, you might want to call some of these methods, these methods directly. Okay. Similar here, these are more internal methods of NetPyNE, but again, they're available to the user. And now we come to this structure, which is one of the main things I want to focus on, and that we will navigate through in a second in the Google Cloud. So this is the structure that I mentioned yesterday. So at the top level, you can access this large main object here called net via sim.net. And through this object, you can access all the information of the instantiated network, including all the actual neuron objects. So below sim.net, you have cells, which is the list of cells. Each cell is of the type of the class cell. And inside the cells, you have these 3 or 4 things. You have the global ID of the cell. You have some tags, some properties, like the cell type, the XYZ location. You have the sections, soma, dendrite, each of them with some more information inside. You have the connections. So the list of connections that target this cell will be available through this structure. And you have the steams. Also, if you use these source steams and target steams, they will be stored here. So the current clamps or the net steams that project here to this cell, they will be stored in this structure. If you go down the way of the sections, inside the sections, you have all the parameters that you define from the high level, the geometry, topology, the mechanisms, and so on. And for each of these objects, you have one of the entries in the dictionary, which is called H object. H meaning from neuron, because you import from neuron, import H. And for example, in this case, for the soma, you would have this section, the H.section object here. So if you wanted to modify anything directly at the neuron low level, you can go into this object and make changes. Ideally, you have to know what you're doing, because you don't want to get sort of the NetPyNE model Python structure that surrounds this object out of sync with what the object is doing. But you can modify them if you need to. Okay, and for the connections, you would have the H object will be the netcon. And I'm actually missing here. You also have the synapses. So here you'll have a list of synapses as well. Okay. Analysis and plotting. So I think Joe is, after this session, he's going to show some of a list of the plots that we have and some of the analysis examples. And that's it. So yes, we can leave now here. Okay, so now I'm going to go to one of the examples we were using before. Okay. Let me check one thing. I think something's missing. Here. 1 second. Okay, so I'm going to show first the basic structure of what happens when you create a model. And then I'm going to go through the importing cells tutorial that imports different types of cells. And we're going to see how they're represented also internally. Yes, run this. I think there might be some issues, but okay. So for example, for this, I can just go to the one we're looking at before with this, the NetPyNE Steam. And this one had a bunch of weird stimulation, but I can just look at the cell representation. So if I go at the end of the simulation here, and we were actually already looking at this before. So we have the basic top level would be sim.net. Okay, so this is, as you see here, of the type class network. Inside here, if we look at the diagram, we have cells and we have pops. Here. So sim.net.pops gives you a list of the populations in the model. We have the S population and the M, and each one is of a type pop, of the class pop. Okay, so if you go into the S population, this is of the type pop, and you can do tags. Tags give you some properties of the cell. So you have this population is of the cell type pyramidal. It has 20 cells, and it's the population called S. You also have something called cell GIDs. which gives you the global IDs of the cells inside this population. And this is quite useful for many things. If you want to do some kinds of analysis, you might want to know, in many cases, which are the cells that belong to each one. So you can iterate this dictionary and get these values.
You were just looking at, you were just looking at a object before this, right? And so with that, if you wanted to access the information from that, you do a dot notation?
In theory, yes. Yes.
Okay.
So this is the difference and why we are using these ODICs. Instead of having to write the bracket, comma, you can just use this dot notation, which can be convenient at some points. Okay, so that's the POP structure. And notice we don't have the cells inside each of the POPs, so the hierarchy doesn't go in the sense that we include the cells that belong to each population inside. And that was a decision that was made initially, and it made more sense to have it this way for many reasons. But you can still kind of access the cells of each POP because you have access to the cell VIDs. So something important here is that the cells are ordered by their VID. So if I do cell 0, this and see the tags, this, oh, sorry, and see the cell VID. Sorry, VID only. Okay, so this is going to tell me that it's the VID 0. So the global ID of this cell is 0. The global ID of cell 100, we don't have so many cells, is 10. For 10, it's 10. Okay. This is also quite useful when you are doing analysis and exploring and so on, because just by the index of the cells list, you can access the cell corresponding to that global ID. So, for example, say we want to access the first cell of the population S. We could do something like sim.net pops S, cell VIDs 0. Okay, so we're looking at the population S, the list of cells inside that population, and we want to get the first cell inside the population S, and then we look at that in the cells list. So this tells you this belongs to the population S. Does this make sense? Any questions?
I have a question. That
Okay.
coordinates of x, y, s, zeta. This is the coordinate of the cell. The cell is not a point. It's like the summa, the center of the summa, something like that.
The center of the summa, exactly. Yes. And notice that it's in both absolute and relative normalized coordinates. Okay, so let's see a bit more of what you can look at inside the cells. So we said we had, let's show here the structure. We've looked at the global ID, we've looked at the tags. So let's look at these sections, sex. So if you just show this, it's going to show the whole underlying structure. And it's also showing you this in a sort of reduced way. You see it doesn't have the quotes here. That's also by design, so it's a bit more clean. Usually, if it's outside the column, it would show you this on a sort of vertical arrangement, one below the other. But at least it's a bit cleaner that you don't really have the quotes for all of the keys of the dictionary. Something you can do this because this is still a dictionary, is use keys to see the names of all the sections.
Sorry, can I ask you something?
Yes.
Is there any way we can do that in a more readable way?
Which part?
The previous one, the sex. For example, I would prefer to have all this information vertically.
To have this information, how?
Vertically. I mean,
yes, that is what I just mentioned. So it usually shows up vertically, but I think this is something due to the collab. But if I run it here, IP. Let me just run the example here, and I'll show you in a bit. It usually shows one below the other. Yeah, and I also show that you can use this keys command. It shows a lot of rubbish here at the end, and I think a lot of this is also because we're in collab. All this stuff that starts with an under script that's not really part of the biological components of the cell. So the only section here is the soma. Okay, so then we can then access the soma, and we can also do this keys thing to see the different components inside the soma. And we see that we have the mechanisms, we have the geometry, we have the H object, which contains the section, the topology, and the synapses. Okay, so just to show you the H object, for example. Well, this is actually the representation that you see for a section, but here, because this is a section, you can do things like 0.5 to access one of the segments. So now you're in a segment, and you could do .hh, I believe, and that is the HH component, and .NA maybe. No, that's not it. It's ENA, for example. Let's see. So I think you can do this at this level. No. Let me see if I can get the intracellular. Oh, because this, sorry, this is the HH, so the variable names are a bit different. Let me see if I can figure this out. This is, sorry, 0.5. We have the HH. So we can do, something we can do to inspect these objects is this dir function that gives you kind of the inner stuff. So GNA, for example, we should be able to do. Okay. So we're getting the conductance of the sodium channel inside the HH directly from neuron by accessing the neuron section, the segment inside the section, the HH object, and the sodium conductance. Okay, so we are here. Let me just show you. Oh, you don't have access to what I'm seeing on the other screen, but I'll copy it over. .net.cells 0 6. No, it's not that nice, but second. Okay, so this is the kind of structure you get. I'll paste it here so you see. I used this pretty print, which usually shows you things in a nicer way when you print the entries of this dictionary, the sections dictionary. So you have one section here, the geometry, and so on.
Oh, thank you.
Maybe we can also use pretty print here, actually. For print. Okay, more or less. The thing is you'll get all this crap here at the beginning. I think that is because we are inside the collab, but essentially the information you want is right here.
And if you want to get access to the output.
Yes, I'll show that in a second. I'll just finish quickly with the cell. So we have seen the mechanisms. Let me just show the connections. So the connections is a list. So if we have a look at the first connection, for example, we see the information, and this is also useful for many analyses. Delete this cell. So you see the first connection has the pre-ID, which tells you the source of the connection. In this case, it's a net sting. So it doesn't really have a global ID because it's one of these net sting that is generated as a stimulation. It tells you the section, the target section is the soma, location 0.5. It's using the synaptic mechanism excitatory. This is the weight that it's using, and in many cases, these weights, you won't know their value until you have a look at this structure, because you are using these connectivity rules, which are very high level. So they generate weights based on these mathematical expressions, for example. So to know the actual values of the connections, you can look inside this structure here. The delay and the label of the presynaptic input. In this case, we know the stimulation is provided by this thing called input 4. And you also have access to the netcon object here. Okay, so I think that more or less gives you an idea of what you can do with sim.net. We also have what I mentioned before, sim.sim data. And here we can see the keys. So removing all the crap at the end with these underscores. And these also are some weird functions. Basically, the useful components here that you have are these four. So you have the spike times, SPKT, the IDs of the cells that are spiking, spike ID. Both of these are lists, and they go together. So if this has 100 spikes, this list will have 100 entries, and this one too. This one will tell you the spike times, and this will tell you the ID of the cells that are spiking at each time. The voltage soma that we recorded, and if you go inside here, you will have an entry for each of the cells that was recorded, and the time that was recorded. So this gives you the time step, really. So let's look, for example, at these spike times. It's recorded as a vector. So you can just do, for example, list, because we're using the same data types that Neuron uses internally. So you can do list of spike times, and you see you get the list of all the spike times. And if you do spike ID, you get the IDs of the cells that spike at each of those times. So with the ID 2, 4, 5, 8, and so on. Yeah.
Oh, I was just wondering whether these things have doc strings, right? So could I do help sim.data, sorry, sim.simdata.spike ID?
The methods and the functions, they all have doc strings. They are not all completed, but they do have the doc strings. They're not all filled in. Mm-hmm. The data structures themselves, I don't believe we have doc strings for those. I don't even know how you add a doc string to a data structure, to be honest.
I'm sure there must be a way, but yeah, it's probably not straightforward.
But there is a bit of documentation on this in the website. Let me just show you that. This is one of the things we are working on, providing more details on this. NetPyNE.org. So in the package reference, where it says NetPyNE data model, here it talks about a bit about this dot notation and how you can use it. Gives you some examples, and then describes the cell class. And I think at some point you have also the sim data. Yeah, no. This is all we have here. So yeah, the sim data structure might not be detailed anywhere. So that is definitely something we have to add to the documentation.
Yeah, I guess sometimes when the variables are, the names are obvious, or obvious enough that you can make a guess, but sometimes
I don't think these are that obvious, to be honest.
Well, Soma is obvious, right?
Yeah. Yeah, so hopefully that this video helps also for the future, but we really want to add some proper documentation for this. So inside vSoma, vSoma, these keys here will correspond to the labels you give to here in record traces. So this is why it's called vSoma. And as I mentioned, you will have an entry for each of the cells that you record. So here recorded from cell 0 and cell 20. Notice that to specify these two cells, we used this sort of format here. We said the first cell from the sensory population and the first cell from the motor population. When we're plotting the traces, we say include these cells. But when they are storing the data, SIM data structure, they are always stored by their global ID, by this GID property. So it turns out to be cell 0 and cell 20. Cell 20 is the first one of the motor population. Okay, so yeah, if you go inside, you just have the voltage starting at -70 and so on. You can use the data, the t here, the time, to plot against the voltage. So you have both the x and y values. Okay, you have some integration small errors. And what else do we have here? Oh yeah, if you record the LFP, you would have it here as LFP. Here we don't have one. And I think that's about it. Okay, so let me think. Okay, so let's move now. Well, any questions about these data structures?
Yes.
Mm-hmm.
If I want to change some, let's say, I want to change a property of the cell. I have my population. I want to change the parameters of one cell, let's say, individually. After, so I believe would use sim.create first, so everything is created, and I would change the Hawk object because I know how to access that, but I believe that's not the better solution, or that's the way.
So the reason that you might want to do modifications after you create a network, it's because it's something that, well, either because it's something that you cannot do via NetPyNE, and you have to do it at this lower level, directly in Neuron, or because you want to modify it during the simulation, which is maybe what you mean?
No, I just, let's say I want to change that that hh.gna of one
because
of
you
the
want to change it only for one cell. That is why you want to access it this way.
Yes.
So you can do it as we are talking about, like directly accessing this way. Soma, you would go to the H object here, and as we did before, to the HH channel and GNA or whatever. You can do 10. You can assign the values directly here, and that will work. If you create the network before, then make the change, and then run. So it would be something like sim create. So this would have to be 0.5. So you access the sim.simulate, sim.analyze. Okay. So this is generally the structure we use to modify things via Neuron, and you can do almost anything here, changing the stimulation, changing the connections, whatever. We also have built-in functions in NetPyNE to make these modifications, and if possible, they're better to use those because they also change the Python structure around the Neuron object. So here, if you change the GNA, the actual representation in NetPyNE, which is at this level, let's see, MEX, HH, GNA won't change. So you will have a discrepancy between the neuron value and the NetPyNE Python structure. But if you use this method, sim.net modify cells, I didn't talk about this function, but we do have this one in the right here. So the structure for
Okay.
Sorry, I lost my connection. I'm trying to reconnect.
Salvador, you're muted.
You're muted.
Sorry, yeah, I lost my connection. Not sure why, but it kept recording, so that's good, and you're all here. So I was saying you can use this modify cells method, and the structure is that you just include the parameters that you want to modify. Let me check, because I think there was also some kind of conditions you could use.
Salvador, I can't see your screen right now.
Yeah, of course. Your window here. Okay. So yeah, so the idea is, signed up. You specify here a dictionary with the properties that you want to modify. So if we wanted to do the same thing as above, it would be soma, mex, HH, GNA 10. Okay. And the main difference is that using this method, it changes the also the Python structure, both the neuron and the Python structure. And I believe there is, so I think this has to be sex, like this. And we have another structure, which is conditions. So you specify which cells you want to modify. Conditions, and you can say, I think you can do something like op S, for example. So you modify the cells in population S. Yes.
So can you access this as a with the dot notation as well when you're specifying it this way?
No.
No. Okay.
Okay, and the same way you have modify cells, you have modify connections. And you can do that at a, also for conditions that you specify for the connections. Let me see the example here where we have reference. Yeah, you can modify the synapses, you can modify the connections. So for the connections, you can specify, for example, the name of the connectivity rule that was used to create that connection. As one of the conditions would be the label. So for example, here, this is all a bit advanced, but I guess it's useful. So we have, we don't have any connections here. So in this example, we don't have connections, but for example, here. So this here is the name of this rule. So you can use this in the modify cons function. You can pass this label as the conditions of the modify cons, and then only the connections that were created with this rule will get modified by that function. Okay. There's, that's a very specific use case, but it might be useful in some cases. And actually, the tutorial one, what we were supposed to do today as well, which is this one that says modifying the instantiated network interactively. That shows this is a simple network with two populations, or one population that is recurrent. And what we do is, after creating and simulating, we get this network. We use this command here, modify the connections. And we say we want to modify all the connections that were created using this connectivity rule, the hop to hop, hop field to hop field. And we want to change the weight to 0.5. Okay. So the initial weight, I think, was 0, 0, you see here, hop to hop. And then we run the network once, we see what happens. And then we make a change to that connection, and we can run again. So notice that because the network is already created, you can just add these commands, which are a way to run. So this is similar to doing sim.simulate. This is even more granular. So you run sim, you gather the data, you save the data, and you plot. Okay, you can do it at this level as well. And you would get a different output. So there's like more synchrony in this case, because you added like a recurrent connection. Okay, so that's a lot of information.
Okay,
at
perfect.
least you know
Thank you.
where to find all these things. And I wanted to show this tutorial of importing cells. We have only 10 minutes, so I will at least give an overview of it. Okay. So we've talked mostly about, let me put this part first. We've talked mostly about Hodgkin and Huxley cells, and then these integrate and fire neurons. But there are many different types of cell models out there. And so this tutorial here shows ways of importing many different cell types. So the idea, what happens when you call this NetPyRams import cell params function? So usually when you define a cell params or a cell type, as you've seen, we create a dictionary with all the stuff that goes inside, the mechanisms, the morphology, and so on. Instead of doing that, you can call this function, import cell params, and NetPyNE will attempt to read the file that you pass on, which would be a file, usually a Python file or a Hawk file, that contains the definition of a cell. So NetPyNE will try to create that cell in the background, read all the information from the cell, all the parameters, all the mechanisms, the morphology, and so on, and store it in the NetPyNE format internally, in the same format that you would define using the dictionary. So this is useful because most of the cell models we're going to work with are already implemented. They're in Python, and they are usually very complicated and have very complex morphologies. So it doesn't make sense to try to enter it manually. So we use this a lot. The first example I'm going to show here is importing a simple Hodgkin and Huxley cell. And maybe you can show the structure of the cell first. Okay, so this is the cell file. Right, we can see it here. Okay, so this is very basic. It's similar to what we're looking at on the first 2 days, where we have a class called cell. We have a constructor that calls a bunch of functions to create the cell. They're actually mostly empty, I think. And it adds like a synapse. Sorry. So this is what they call an abstract class called cell that has a number of things. And then we have another class called HHCell class that inherits from the cell class. So this is a bit more of an elaborate implementation, but you don't really need to worry about that. The basic idea is that we have a class in Python that defines a neuron in the neuron language. So it creates the sections, the soma and the dendrite. It adds some geometry in the same way that you were doing it the first 2 days. Adds some biophysics, the HH channel and the passive for the dendrite, and connects the dendrite to the soma. Okay, very simple structure here. So let's see what happens when NetPyNE imports the cell, and I'm gonna comment everything else. Has anybody found how to add comments here in Google Colab? The only way I found is just cutting. Well, anyway, so I'll just cut this and run. What happens? Complaining. Oh, I didn't. It's complaining about something that oh, okay, because I'm trying to plot the traces of something that doesn't exist. Okay, sorry. Okay. Select text and then command +/. Okay, great, thanks. Okay, so now this thing ran, so we can explore the structure of net params in this case. Okay, so notice that what we have here is net params, this high-level structure that we then pass to NetPyNE. Okay, so inside here we have cell params, and we already see what is contained inside cell params. So we have one of the entries. We look at just the keys of the dictionary. We see we have just one entry, which is pyramidal Hodgkin-Huxley. So we can look at this entry here, HH, and inside we have all the stuff. I don't like how this is printed. Let me try with this pretty print again. Okay. Okay. Okay, so notice that this cell params peer HH is what NetPyNE generated by itself using this import cell command. So we told NetPyNE, go to this file that is called hhcell_file.py. The name of the cell inside this file is hhcell_class, and we saw that here. Here. So we have to tell NetPyNE what is the name of the class, and essentially extract all the information you can from here. So it doesn't do it by reading the text file itself, but what it does is creates a copy, an instance of this cell, and then deletes it from memory once it has all the information. And we see that what it was able to extract from this cell is what is shown here, which is it has a soma and a dendrite. So this, of course, will match with what we have on this side here. So the soma has GNA bar 012. We see that right here, GNA bar 012, 03, and so on. And now it's in a format, in the NetPyNE format, so it's in a declarative format. It's in dictionaries and lists. And now it can be used to create, for NetPyNE, to create the same types of cells that you have here, but using the whole NetPyNE architecture. Questions? Okay, so let me paste this back. Of course, you can then just create a population that we call here HHPop using the cell type that we just imported, this PRH, and create as many copies of that cell that we just imported as you want in your network. So we have 5 minutes. Let me run quickly over some of the other cell type examples. Okay. So we have the Hodgkin-Huxley. We have this one, which is importing from a Hawk file. And let me just quickly show you how the Hawk file looks. This is geom.hawk. Okay. So you also have to specify the cell name, which in this case it's something called template. So in Hawk, when you define these templates for cells, they're called templates. Begin template E21, and at the end, well, a big cell, you have end template E21. So yeah, on the side of the user, this works exactly the same. You just tell it the name of the Hawk file. Sorry, here the name of the Hawk file, the name of the template. I didn't mention this, but you can either decide to import any synapses that are present or not. If you want to use them, you can import them, and they will be added to the synaptic net params structure in NetPyNE. So let's see what happens when we import this one. I'm gonna comment all this stuff. Command Shift 7. No. Command 7. No. What was it? Command +/. No, doesn't work for me. Anyway, just to comment this out. Cut it. Okay. So if I run this, and I now look at PRHH3D, because this one is like a long cell. What happens? Oh, PRHH3D Hawk, sorry. Okay. So you see that it's a very long structure that is being populated there because it's reading or printing all the 3D points that are taken from this file. So NetPyNE has that now extracted all that information and stored it in these internal NetPyNE structures. So you see, for example, in the Hawk file, all the 3D points were defined using this pt3d-add Hawk command. But in NetPyNE, they're now in a declarative format inside a list. So for example, for dendrite 63, you have the geometry definition and a list of 3D points. Okay. So now you can use this morphology as well, this cell with this very complex morphology in Neuron. Whoa, this was very long. Let's maybe quickly have a look at another one. And yeah, let me comment on some of the things we did here. So notice that I imported the cell, and that is going to be stored in cell params, net params, and this label. But I also temporarily stored it in this variable, cell rule. So this is just a pointer to the same cell params. And then I can modify things in NetPyNE. So say I don't really like the stuff that I imported and I want to make some minor changes, I can use the NetPyNE structure to modify some of the channels, for example. Okay, so the soma, I want to change these parameters. And yeah, this is another way. I iterate over all the sections. So for sec name in cell rule sex, all the sections in this cell that I just imported, and I change the passive mechanism to have these values and the membrane capacitance to be 1. Okay. So this allows you to modify any type of existing cell. You can just import it into NetPyNE and modify it using the standard language that you already know in NetPyNE. I don't have much time for more, but here is a bunch of other cells. So we have this Traub model, which is implemented in Hawk and has some peculiarities because it doesn't really, what was it? Oh yeah, the summa is called something different. It's not summa, but summa with a capital letter, so you have to change a couple of things. You had this mainen cell, which is in Python and has some weird dynamics. The same for the Friesen cell. Here in the Friesen cell, we did something that somebody asked yesterday, which is specify that the spiking location, the origin of the spiking location, is not the summa, but the axon. And you do that in this way. So you say the section that you want to be the source, you add this property, spike generation location, and you say at which location of that section you want it to be the origin of the spiking. And then NetPyNE will make sure that is where you check for the voltage threshold. And then at the bottom, you have importing of 3 or 4 different types of ECK-rich point neurons, but they are implemented using sections. So it's a kind of a weird combination that I mentioned. I'm not very interested in teaching, although if you are interested in using these cells, you can follow this example. Okay, and then we just create populations of each of these cell types that we imported, and we can even connect them to each other. This is actually, let me remove, this is legacy, you don't need this. Okay, any questions? So I know this was all a bit intense, but I just wanted you to have an overview so that you know where to look for things. Yes, sorry.
I have got one because I cannot see. Can we import a mode file from Neuron? Say, I can see that we can import a .hoc file, a .py file, a .mode file. Can we?
So mod files are the files that are used for mechanisms, so for channels or for synapses. Yeah. And so the way they work is that you have to compile them beforehand, and that for that you have to use Neuron IV model, which is what we did here.
Okay.
And as long as they are compiled before you sort of start the Python kernel you're going to use, they will be available inside your Python kernel. So the only thing you need to do is compile them beforehand, and they're available both in Neuron and NetPyNE. So in NetPyNE, we are using lots of different mod files. So for example, here, for these examples, we are using a lot of mod files. You will see here lots of different channels. These are calcium channels and so on. And they are just available directly to NetPyNE in the same way they are available to Neuron once you compile them.
Fantastic. Thank you.
Suri, I have rather nice query. The cells are connected via synapses in NetPyNE, that is chemical connections. Bill had spoken electrical connections like gap junctions. Can those be implemented in NetPyNE? Yes. We have a tutorial, I believe, or an example with gap junctions. So when you create the connection, you have to do something like, say here, gap junction. And I don't know if it's just true or something else. So I can point you to the examples for that if you want. Any other questions? Okay, thank you so much. So we'll come back in 10 minutes maybe to have a bit of a rest. So 3:35, and Joe is gonna show some of these analysis functions. And then at 5, we'll have some exercises on some of this stuff with Erica. Thank you so much.
Thank you. Thank you.
Thank you.